In this video, we're going to talk about bending strength of beams and lateral torsional buckling. Recall from the last video that when a beam is not continuously laterally supported on the compression side, lateral torsional buckling may occur. Recall that in this beam, for example, the top flange is in compression, so it wants to buckle, causing the beam to deflect laterally and also twist, which is why it's called lateral torsional buckling. Recall also the concept of compact and non-compact sections. A compact section is one where yielding occurs before flange local buckling, and a non-compact section is one where there could be local buckling of the flange. Let's explore a little more about lateral torsional buckling. Here is a beam, actually in the structures lab at UB. This is called a gantry beam that supports the crane, and you see that this gantry beam is not continuously laterally supported. Let's look at a bridge girder. We've talked about this a lot in past assignments. So somewhere over here, there's going to be a positive moment, and therefore the top of the girder is going to be in compression. And if that wants to buckle out, the deck is providing it continuous lateral support. So for the positive bending moment, the beam is continuously laterally supported. On the other hand, if we look at this region here that has negative bending moment, then the deck is not, the compression is at the bottom, and the deck is not laterally supporting it. So lateral support is provided by cross frames, and so there is a distance between cross frames over which the beam is not laterally supported. So in this region, deck provides continuous lateral support. In positive moment region. And the negative moment region lateral support is provided by cross frames. And so this is not continuous, and the distance between cross frames is called the unbraced length. So over the unbraced length, in the unbraced length, the beam is not laterally supported. It's only laterally supported at discrete points. Now, during construction, the deck hasn't cured yet, as seen in this figure. The deck hasn't been poured here, but even when the deck is poured, it hasn't cured yet. So even in the positive moment region, there isn't continuous lateral support, and lateral support is provided only by the cross frames. So during constructions, lateral support provided by cross frames in both positive and negative moment regions. So the AISC manual provides a curve to determine the strength of the beam, or the nominal flexural strength of the beam, when there is the possibility of lateral torsional buckling, and also when there is the possibility of the section being non-compact. So on the horizontal axis here, we have unbraced length. So this is the distance between lateral supports. And on the vertical axis, we have the flexural, nominal flexural strength. We notice that if the beam is continuously laterally supported, which means the unbraced length, we can think of the unbraced length as being 0, and the section is compact, then the flexural strength of the beam is the yield stress times the plastic section modulus. So for a beam that is continuously laterally supported, and made of continuously laterally supported on the compression side, and made of a compact section, the nominal moment capacity equals the yield stress times the plastic section modulus, typically about the x-axis because the beam is oriented to bend about the strong axis. This is the nominal moment capacity. This is the yield stress. And the plastic section modulus. About the axis of bending, which is typically the strong axis, the x-axis. And in other places, we see that the curve looks more or less like the column strength curve, because the phenomenon is the same. It's one of buckling. There's another quantity here, CB, which has to do with, this is called the moment gradient factor. And this has to do with how uniform the bending moment is in the beam. So these are some things that you will learn much more about in the steel design course. For our purposes, we'll just take simply CB equals 1. So if we want to determine the nominal flexural strength or the moment capacity of a beam, then we would look in this curve, and given the unbraced length, we can go and calculate what the moment capacity is. Again, as we did in the case of the column, instead of doing this for the purposes of this course, we will simply use tables provided in the AISC manual. So we will only consider cases for which tables are available. In the next couple of videos, we'll look at how to use these tables.